here. So that depends on whether we have time or not. Okay, fine. So before going into a del operator, I need to just mention something called as line integral and line, surface, and volume integrals. Okay, so this we have line, surface, and volume integrals. Okay, so what does it mean is before explaining this integral, assume that you are standing in front in the back of somebody. So there is another person standing here, and let's say you are pushing this person with a force. So you know that the force is towards the right. So you can represent that using a vector actually, and the length of the vector will give you how much force you are applying. So this is a representation where you show that okay, this much is force is applied to that person, and this much is this is the direction of that force. Okay, and so depending on how much force you exert on that person, the person will move forward or fall down depending on how much force you exert. Okay, so you see that you can represent this using something with a diagram, which is basically this arrow. And this arrow, you can say, is kind of something called as a flux. So it can be a force, or it can be any other vector quantity. So if you group all these forces, you can call this as a field or a flux. For example, let's say you have a big wall, okay? And there are people standing at the side of the wall, okay? And they are all pushing the wall, okay? So if you represent the force of each person, so basically you can represent it something like this. A different person will push with different force. So the length of that vector line will be different. So you can see that if you eliminate the persons and the wall, finally you end up having something like this, right? That's a straight line. It need not be straight line. And this is something called as a collection of a vector quantity. And this is called as a field. Okay, this is called as a field. Now remember, the field need not be in a linear direction. For example, it can be like this. Okay. For example, one person might be slanting, and he might be applying the force, something like he'll be pushing for some time, and then he will be relaxing and pushing for some time, something like that. So it will not be a linear thing. Okay. And this representation, so this collection is called as a field, and these lines that we see which shows you the vector is called as a flux. It's called as a flux lines. So flux lines is a general term. In electrostatics and magnetostatics, it is usually used to represent an electrostatic field or a magnetostatic field, or in mechanical terms, it is mostly a force. So electrostatic or magnetostatic basic field is a force. So basically it's a force. So whenever you see such different arrow lines in different direction, you can assume that it is kind of a force which is traveling in different directions. For example, if you stand over these lines, then because of the force it is getting exerted, you will be traveling along this line. Okay. If you stand here, somewhere here, then you don't have any force being exerted, so it will be at the static position. Okay, so whenever you see some flex lines or a field, you can see it as some kind of a force being exerted at that point. Okay, so with that understanding, let me define this line integral. Assume that there is some kind of a wire or a line like this. Okay, this is a point B and this is a point A. And there is some kind of a field which is there across this line. Okay? Some kind of a uniform field or it's a uniform vector. Let's say it is A. Okay. So each line it is basically a vector. And this is a path which is L. So this is not a closed path as of now. Therefore, this is path L. Okay. Now line integral is basically if you take a small distance dl, okay, where dl is a vector, and the direction of that vector is tangent to the line. And if you find the component of the vector A along each of this tangential path as each of this line, and you integrate along the line from A to B, that is the line integral. Okay, so let me define that in words. So the line integral L A dot dl, where A and L both are vectors, is the integral of the tangential component of A along the curve L. Okay, so basically what we are doing, we are considering a dl at different instances of this line. Very small distance. Okay, and the A is passing through each and every point. Assume. Okay, then you can see that you want to find out how much this vector A influences the path A to B. For example, the A can be an electrostatic potential, and the A to B is a wired line, is a metallic conductor. Now you need to find out how much is the influence of this electrostatic potential over this line. So what you will do is you will find the component of this electrostatic potential over the line along the length, small length dl, and you add it up from A to B. Basically, finally, add it up means you are doing an integration. Okay, so the notation is something like this: integral A dot dl. This is called as a line integral. So this is, so the limit is from A to B. So this can be represented as the magnitude of A into cos of theta into dl, where theta is the angle the dl is making with the vector. So at different points, it might be making a different angle. Right? This is called as the line integral. Now, if the path you are considering is a closed path, like this, so it is closed, then your integral will change into a closed integral along the path L, A dot dl. So here you are basically finding for each point in that path, in the closed path, how much is the influence of the vector A on the path. And this is called as the circulation. The circulation of A around L. Okay. This is called as a line integral. So similarly, let's say there is a surface. Okay. And let's say there is some vector A which is passing through a surface. Okay. So it need not be over the surface. It can come from under the surface, cross the surface and go outside. In any way it can go. So just for the sake of drawing, I have drawn it like this. Okay. Now, if you consider a small square of size ds, okay, whose direction is perpendicular to the surface, it is denoted as an cap. Okay, so n cap is a unit vector which is perpendicular to the surface, and ds is a small element of the surface. So an cap is a unit vector perpendicular to the surface. So whenever you see a surface, it has a direction and it is always perpendicular to the surface. So it can be either upwards or downwards depending on the situation. And this A, you want to find out how much A influences the surface. Okay, so that what you do is using the surface integral, we denote as psi, is integral along the surface S. Assume that the surface is S. A dot an cap ds. Okay, so this is called as a surface integral. So here you should note that I haven't put a arrow over ds because the direction is already given by an cap. Or you can, if you don't want to have an cap, you can directly give a dot ds bar, where ds bar is equal to an cap ds. So this is called as a surface integral. Okay, and this shows the net outward flux through S. So line integral showed me how much is the circulation of the vector along that path. The surface integral will give me the net outward flux. For example, flux, let's consider a surface in which the vector is going like this, crossing the surface. Some vectors are going downwards, crossing the surface. Okay, so and when you do the surface integral, what you do is you take a small piece ds of the surface and then you integrate for different values of the vector, which is a. So if you see, this is actually some flux lines. Basically, the collection of vectors is a flux, and you see there are many flux lines. And if you see the net flux of the surface, there are 3 flux lines coming out and 3 flux lines coming out to the bottom. And if you have some flux lines going inside, which is not coming out, so the net flux is 1. Basically, the 1 flux line is there because there are 3 flux lines coming, 6 flux lines which is coming out and 1 flux line coming in. So basically there are, finally you have 5 net outward flux through S. Okay, so we'll see this in detail. Don't worry about this now. Okay, similar to surface and line integral, there is something called as a volume integral. Okay, so if you have a volume, assume that there is a cube. Okay, and the volume integral is given by rho v dv. Okay, so rho v is some kind of a scalar. Okay, so basically you are considering, you can consider a small strip of cube inside this cube, and you are integrating this cube all over the bigger cube. So that is basically the volume integral. Okay, so volume integral doesn't have too much of a physical meaning, but surface and line integrals have a physical meaning. Fine. Now let's go to the del operator. So I told all these surface and line integrals because it will come in one of the theorems, so that You can understand when I state the theorem. Del operator is denoted by this sign, inverted triangle. Okay. In Cartesian coordinate system, the del operator is given as dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z z cap. Okay. We'll see one example so that you understand this. And del operator operates on a scalar. So this is also called as a gradient operator. So I hope you know what the operator means. For example, plus is an addition operator, minus is a subtraction operator, cross is a multiplication operator. It does some kind of an operation. Whenever you see a plus, it means that you need to add the left operand and the right operand. Similarly, whenever you see a multiplication, you want to multiply the left operand and the right operand. Similarly, del is an operator which operates on scalars. So what is the specialty of del operator? You see that the output of del operator is a vector. So why it is a vector? You see the del operator has a unit vector along each of the directions. So output of a del operator is a vector. It is also called as a gradient operator. Fine. So this is in the Cartesian system. Similarly, you can define del operator in cylindrical coordinate system as del is equal to dou by dou rho a rho cap plus 1 by rho dou by dou phi a phi cap plus dou by dou z a z cap. So you can derive all this expression. I am not going into derivation. It is out of your syllabus. So, okay. So make sure you understand what that operator in cylindrical coordinate system is. Similarly, in spherical coordinate system, you define del as dou by dou r ar cap plus dou by dou theta, sorry, 1 by r dou by dou theta a theta cap plus 1 by r sin theta dou by dou phi a phi cap. Okay. And del operates on a vector, or sorry, on a scalar. Okay. So we say the gradient of a scalar v is written as del v. For example, let's say v is equal to x, y, z. Means if you consider a Cartesian system, v at any point is the multiplication of x, y, and z coordinates at that point. So let's say this is 1, 2, 3. So the v at this point is 6, which is a scalar. It has only magnitude. Let's say this point is 1, 1, 2. So the v at this point is 1 into 1 into 2, that is 2. Okay. So this is 1 multiplied by 2 multiplied by 3. This is 1 multiplied by 1 multiplied by 2. So you see that in this coordinate system, so we are considering the Cartesian coordinate system, the vector, sorry, the scalar v at each and every point is the multiplication of the corresponding coordinates. So this is for an example. Now, when you do del v, okay, so what is the explanation? It is dou by dou x ax cap. So this is equal to dou by dou x into v ax cap plus dou by dou y into v ay cap plus dou by dou z into v az cap. Okay, now let's substitute the value of v. So this is dou by dou x into x y z ax cap plus dou by dou y into x y z into ay cap plus dou by dou z into x y z az cap. So when you do the partial differentiation of the first one, you will be considering x as a variable and y z as constant. This is y into z ax cap plus x into z ay cap plus x into y az cap. This is del v. Now you see this is a vector. Okay, so now if you have in the Cartesian coordinate system, okay, at the point 1 comma 2 comma 3, your value of del v is equal to, you substitute the corresponding values, y into z is 6 ax cap plus x into z is 3 ay cap plus x into y is 2 az cap. Okay, and now this point, now which was a scalar, has a direction, and the direction is along x you have a magnitude of 6, along y you have a magnitude of 3, and along z you have a magnitude of 2. Okay, so now that quantity at that point now has some magnitude. Similarly, at the point 1 comma 1 comma 2, you will have del v is equal to 2 ax cap plus 2 ay cap plus 1 az cap. And so this point now also will have some directions. So the del operator converts a scalar into a vector. And when you do the operation del into the scalar, this is called as the gradient of a scalar field. Field means you have multiple points v. So del v is called as the scalar gradient of a scalar field v. And the gradient has a property which is the gradient of a scalar field v is a vector that represents both the magnitude and the direction of the maximum space rate of increase of v. Okay, so what does it define? A gradient means it represents both the magnitude and direction of the maximum space rate of increase of v. Okay, so if you explain it in a physical term, if you move from, let's say, position A to position B, okay, and so there is some space difference because A might be at some point 0 and B might be at some point, let's say, 2. Okay, and if you move in this from A to B, so you can move in either like this or like this or like this or like this. So you have infinite possible ways. Now, in which direction do you move will have a maximum rate of increase of your scalar. Okay. For example, here in if you move in the x direction, you have the maximum increase because you have the maximum magnitude in the x direction. Similarly, if you consider the next point, which is del v, you see that both x and y have maximum magnitude and z will have the minimum magnitude. So the maximum rate of increase, space rate of increase is along x and y. So the gradient will give you in the direction in which you have the maximum space rate of increase. Okay, if you take any unit distance, at which unit distance you will have the maximum increase. Okay, so that is a concept of the gradient. Now the gradient till now we have considered it is only in the Cartesian coordinate system. This can be represented in cylindrical coordinate system as dou v by dou rho a rho plus 1 by rho dou by dou phi a phi plus dou v by dou z a z. So this is in cylindrical. Similarly, in spherical, it is given as del v is equal to dou v by dou r ar cap. So there should be a cap here. Ar cap plus 1 by r dou v by dou theta a theta cap plus 1 by r sin theta dou v by dou phi a phi cap. This is an expression of the gradient v in cylindrical and spherical coordinate system. Similarly, there are some properties for gradient. The first property being del of two vectors u v plus u is equal to del v plus del u. Second property, del of v into u is equal to v into del of u plus u into del of v. Third property, del of v by u is equal to u into del v minus v into del u by u square. So these properties are basically your differentiation properties. So there is not much in this, but still let's state this. Del v raised to n is equal to n into v raised to n minus 1 del v. Okay. Now, as I told earlier, as per the definition, del v gives the magnitude of the maximum rate of change in v per unit distance, also points in the direction of the maximum rate of change in v. Okay, so those two are the properties of the gradient. And if you assign, let's say, a vector a is equal to del v, then va is called as the scalar potential. So this we'll see in electrostatics, because we see that E is equal to del V in electrostatics. But so this, if the vector that you obtain by doing a del operation on a scalar is called as the scalar potential. Okay, so that is regarding the gradient operator. Now there is a theorem on gradient operator, or before doing that, let's define something called as divergence. So divergence of vector A is equal to del dot A. Okay, so del is dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z az cap. You do a dot product with ax cap plus ay cap plus az cap. So when you do the dot product, you see that this is equal to dou ax by dou x plus dou ay by dou y plus dou az by dou z, which is a scalar, because the output of a dot product is always scalar. So divergence of A is equal to del dot A. Okay, and we define divergence as the divergence of A at a given point P is the outward flux per unit volume as the volume shrinks about P. Okay, so let's say there is a volume of a cube, assume. Okay, now there are some flux lines which are coming out. Okay, and there are some flux lines which are going in. Okay, and the divergence of A at any point P, let's consider a point P, is the outward flux per unit volume as the volume shrinks to about P. So if this cube shrinks to P, shrinks to this point P, what is the net outward flux? So you understand that the flux means basically some kind of a force lines. It can be because of a charge placed inside the cube and a charge placed outside the cube, because a charge always creates a force. Okay? And divergence gives you the net flux at any net outward flux at any point P. For example, let's consider different scenarios. So this is P. Let's say the flux are like this. All are going out. So the net outward flux is 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now let's consider the same point P with something like this. And the flux are going towards P, but our divergence means the net outward flux. So divergence at the point P here is -8. There are 8 flux lines going inside to the P, but our definition of divergence is the flux going outside P, and this is -8. And let's consider one more situation. So here, if you consider the point P, you see that there are 4 flux lines coming to P, and there are 4 flux lines which is going out of P, which means your divergence is 0 because the net outward flux is 0. Okay, so this is called as divergence. And there is, so you can always write divergence for cylindrical coordinate system also as del dot A is equal to 1 by rho dou by dou rho into rho A rho cap, sorry, dou A rho plus 1 by rho dou A phi by dou phi plus dou Az by dou z, where A rho, A phi, and Az are the components of the vector A. So this should be a vector along rho, phi, and z. Similarly, you can do in spherical coordinate system as del dot A is equal to 1 by r square dou by dou r into r square AR plus 1 by r sin theta dou by dou theta A theta sin theta plus 1 by r sin theta dou A phi by dou phi. Okay. All these equations are a bit lengthy, I know, but this is just for the sake of completeness. You might not get any questions from this, but still make sure you know the equations. Okay, just in case they ask. Right. Okay, so I think we will stop it here because I would like to take the theorem, divergence theorem also, but I'll continue in the next class. Okay, so let me take the attendance. Can you give me a minute?